Hello, today we're going over one of the most important chapters from, or sections actually, from all of Calculus 2 in my opinion, and probably one of the most applicable to engineers and, relatively in the real world for mathematics, and that's finding the volume of any function. We know how to find the volume of spheres and whatnot, we know the formulas for them, but a lot of functions don't have a formula, and you have to use some sort of a way to solve the volume, and here's how. This is one of the ways of using it, and it's called the disk method. So basically, with the disk method, like the shell method, it uses a formula of volume equal to pi big R squared minus R squared little r squared dx. And there's an integral from a to b of that. And so basically, what this is saying is it's taking the volume of a rectangle, basically, and it is revolving it around an axis that is chosen by you, and it is revolving it around that in the form of a disk vertically, and so adding up all those small vertical rectangles creates a volume. And so we're going to start off with an example. This is the equation that is basically given for it. You're going to need to know this when it comes to practicing these. But we're going to start with a simple equation of y equals x squared and y equals 4. So we're going to graph that out real quick. And on these problems, I'm kind of just going to stick away from solving the entire thing out. I mean, I'll get to this integral setup, but we learned in Calc 1 how to do that, and I think it's fair that, something like that isn't technically really needed for explaining in depth into a video. I think that's a little bit of a time waster. So as we can see, this is y equals 4 and this is y equals x squared. I didn't include that side of the graph because it's irrelevant to this question. So we got this area right here, and we're going to start off with, okay, we got rectangles, and we're going to go around the x-axis for this one. So the x-axis is right here. We're going to be revolving around here. These vertical rectangles will be revolving around the x-axis. So we're going to start with big R goes from the top of this rectangle down to the axis of rotation. And big R is going to look like just going to be 4 in this case. And little r, we're going to define it out, is equal to x squared. And now we're just going to simply set it up the integral. Now we need to know a and b, right? And so the volume is equal from a to b. Well, we can actually see where does it go to the x direction. Well, as we can see, where's this point at, right? Well, we could just set them equal to each other, or you could just simply look at what is the square root of 4, because if you set 4 is equal to x squared, right, that's going to be 2. So we know that this is at 2. So we're going to go from 0 to 2. And then we're going to say pi times big R, which is 4, minus, and that's squared, by the way, big R minus little r, which is x squared squared dx. And that's the setup for that. Now we're going to move on to y. Oh, we're going to scoot down a little bit. Y is equal to, pencil out. What are you doing? Y is equal to x squared at y is equal to 4 again, right? And here's where it's different, though. In this one, we're going to rotate around x is equal to 2. And so this is where it gets a little more tricky, and a lot of people messed up, and I remember this being challenging for me. But we're going to graph it out again. I'm going to show you how this works so that when people are, and like us, are practicing it, when we're practicing it, we'll see, hey, guess what? It's not as hard as we like to think it is. So this is 1, we'll say that's 2, this is 2, that's 4. So if we go out right there, this is where we're looking to go. And now it looks like we're going around right here. We're rotating around this right here. So this is where we're rotating around, right? So let's go ahead and find something out. Instead of vertically, these slices, or these rectangles, are going to be horizontally. And that's the main key. All of these equations are going to need to change to be in terms of x. So x is equal to, if we square root this and square root that, the square root of y, okay? And for this one, luckily, it's still just going to say y is equal to 4. So now what we're going to just do is we're going to go ahead and take a look at the importances in the first one up here. It was top minus bottom for looking at, you know, the r's. In this case, we're going to look at r, right? And it's going to be left minus right. So remember, r is this longer one, and little r is this shorter part, right? Well, as you can see, we're going to be going from right minus left, right? So that's going to be this right minus this left, right? And that's a good way to think about it, because if you think about it, it's going to be 4, because we're starting over here, or 2, sorry, oh my goodness. It's going to be 2 minus, and then, let's see, this is going to just be the function of square root, or no, it's going to be, this is going to be 2 to, okay, sorry. So if we look at this, we're going to say, okay, we have r here, right? We're going to go ahead and look, okay, where's r stretch, right? Well, r just stretches a complete 2 distance, right? So r is just equal to 2 in this case. And little r is just going to be 2 minus the square root of y, right? So it's just 4 minus that square root of y. So it's basically just going to say we got this portion minus that, or this big portion minus that small portion is going to give us each one of those little rectangles' height, right? And so thus we can set up our integral. This time the limits aren't going to be the same. So if we look at it, we're saying, okay, notice how the limits in the first one for 0 to 2, right? Well, luckily for us, the limits are still going to be 0 to 2 because we're going from, we're actually not going to be 0 to 2, sorry, 0 to 4, actually. So as you can see, it's 0 to 4. We're going to the y-axis because the functions change from y equals x to x equals y. So now it's in terms of the x variables, right? So now, or I mean y values basically, right? So if we look at this, we'll say, okay, we got to get we're going to be integrating from 4 because we're going horizontally, right? So it's going to be from 0 to 4 of pi times big R, which is simply just 2 squared minus 2 minus square root of y squared dy. So now we got to there, and yet again, we see the common thing that we really don't need to move on too much from this. And the last one I'm going to do is the last kind of tricky idea. This up here. And it's going to be y is equal to x squared. Y is equal to 4, just like the previous. But x is going to be equal to -1. So now this is going to be tricky because we're looping around a completely different side. So let's try this, right? So as we know, it's square root of y, right? We're gonna already set ourselves up for that, right? Square root of y is equal to x, and still y is equal to 4. So if we set up our graph real quick, I'm gonna do this one. Got this, right? We're going to be going around this value right here, -1. And this is what we will be looping around, or rotating around, right? So if we look at this and we say, okay, this is one of our rectangles. This is our r, and this is our little r, right? What can we say big R is? Well, as we remember right before, it's right minus left. In this case, we see that the rightmost curve, right, or function, is just going to be equal to the square root of y. So the square root of y minus -1. So that just turns into plus -1, plus 1, basically, right? Because we see that's minus -1, right? And so then we see what's little r, right? Well, little r is actually just the point in between there, right? Well, that's just -1. As you can see, it's just 1 point away, right? So simply put, that because it's squared, it's not going to be a big deal, but r is just going to be 0 minus -1. So it's just going to be 1, right? So as we saw in this earlier case, right, that's just up here for r, that's just 2 minus, up here, that's just 2 minus 0, right? So in this case, it's just 0 minus -1, which is just 1. So now we can just simply, same limits, 0 to 4 as the last one, pi, big R, square root of y plus 1, squared minus little r, just 1, squared, dy. It's that simple. Now, I'm just going to close up here in the last minute, or the last 30 seconds, to explain the importance of this. I could show many other problems, some being really hard and some being even easier than this. I mean, this is a pretty simple one, but the important point is noticing how to set up the r's and the little r's, right? And knowing when to switch the limits and knowing when to switch the functions. And here's the best way of thinking of it. And this works for the shell method too. If you ever see your rectangles horizontal, you know that you're going to need to change your functions from y equals x to x equals y. That's just how it has to be. And when you think of it, it's because it's horizontally, right? And you are going up and down instead of right to left when it comes to integrating. And so horizontal rectangles for both the shell and the disk method must be changing of limits and x equals y. So that's basically it. And honestly, this is one of my favorite parts of calculus too, is simply just finding the volumes. And the disk method is one of the easier ones. The only bummer is when you have where the disk method has to be broken up. And that's for a future tutorial. Thank you very much for watching, and hopefully see you soon. Real quick video. I actually just wanted to show you how to solve one of these disk method problems if you accidentally have where you have to separate the limits. So for example, if they wanted us to rotate around this x-axis here, right? If you look, right? Remember, it's always the r, right? It's always going to be the big R, at least, right? It's always going to be this top, right? Minus whatever's left over right here, right? So if you look at this, right? Or I mean so if you look at this big R right here, right? And you say, okay, he comes down all the way right here, right? That's just going to be, of course, 3 minus, or that's actually just going to be 3, right? So you're just looking from the bottom underneath 3, sorry. So, but when you look at this one, right, the problem is that R does not always stay 3. It also is, at one point right over here, from here on, going to be, the top is going to be 6 over x. So you have to split up the limit. You have to go from a to b, and that a is going to start at we're going to go from x, from here to this x, right? So from 0 to, well, what is that x? Well, we have to look at when the x value, right, of 6, when 6 over x is equal to 3, right? Because that's 3 up there, right? When 6 over x is equal to 3, which is y, right? We can go ahead and look and we can say, okay, if we multiply by x, 6 is equal to 3x, x is equal to 2. So at x equals 2, this is equal to 3, right? I mean, you could plug that in, but whatever. We'll see that, right? So we're going to go from 0 to 2 of pi times big R for this case, remember, we're starting with the beginning area. This simply, it's like a little box right here, right? Big R is just going to be 3 squared minus little r squared, which is just going to be, little r is just going to be 1, right? Because it's going to be top minus bottom, which is 1 minus 0, right? So that's just going to be 1 squared dx, right? Because we're staying in the x direction, or x coordinates, right? So now the second integral is going to be from 2 to wherever this hits 0 at, right? Now, when does 6 over x equal to 0? Right? Because that's when y equals to 0, right? Well, I think we can all tell that by that you can't really solve that. So you're going to have to look at, well, okay, at what point does, x equal or y equals 0, right? Well, 6 over 0 is something that isn't going to happen. And when you think about it and you look at that equation, you're like, wait a second, that isn't 0. Sorry. That is actually just, we're going to 1. So we're going to say 6 over x is equal to 1, right? We're not going down to 0 here, we're going right to there. 6 over x is equal to 1, which 6 is equal to x. That's it. So x is equal to 6. So from 2 to 6, we're going to say pi times big R, which is now going to be 6 over x quantity squared minus, that is still 1 dx. And that is how you're going to be able to solve these equations when you have to split them out by 2. Took me a second there to remember how to do this, but I remembered, oh wait, that's y equals 1. That's about it. Thanks for watching.
Hello, my name is Timothy Organo, and today I'm going to be doing a video presentation on section 7.3 volume, utilizing the shell method. So what the shell method is basically another way to calculate the volume of a solid of a revolution utilizing cylindrical shells instead of the dish/washer method. So as you can see here in this diagram, here we just have a curve or bounds a region over here, and we are going to utilize a rectangle or a cylindrical shell to rotate around the y-axis, which is here is the axis of rotation. And we get this rectangle and rotate it around, which actually produces a cylindrical shape that we're able to calculate the volume of. So over here on your right hand side, this is basically just a better visual representation of how this cylinder looks like with this bar here. And when it's rotated around the axis of revolution, it creates a cylinder. So this right here, R, can be described as the distance from the axis of revolution to the rectangle. So that'd be from this distance here to this distance here. Or as you would see in this picture, since the axis of rotation is y, it'll be from this distance to this distance. So it'll be from right there to right there. And h is just simply the height of the rectangle. So that's this distance from right here to right here. And from in this diagram, it'll be from right here to right here. So furthermore, the circumference of a circle is c equals 2 pi r. And then to find the lateral surface area of a cylinder, the formula is A equals 2 pi r h. So with these formulas in mind, there's actually a formula to calculate the change in volume based off of these two equations. So over here, to calculate the volume, it'll be V equals from the integral of B to A 2 pi r h dr. And then just something very important to note when utilizing the shell method, we just want to make sure that the rectangle that is drawn is always drawn parallel to the axis of revolution. If we were to draw a perpendicular shape, then that would actually be the dish/washer method. So to continue, we're just going to go ahead and start some examples here. So right here, for example 1, it says use the shell method to find the volume of the solid generated by revolving around the region bounded by y equals x to the 1/3 and y equals x to the 4th. So we're going to go ahead and do first is we're actually going to try doing this revolving around the y-axis. So the first thing we usually want to do is set these two functions equal to each other so we could find where they intersect so we can go ahead and graph them. So when we set that equal to each other, that'll be x to the 1/3 equals x to the 4th. And then to solve that, we're just going to go ahead and cube both sides. That becomes x, this becomes x to the 12th. Go ahead and subtract x there. So it becomes 0 equals x to the 12th minus x. And we're going to go ahead and factor an x out of there. So it becomes 0 equals x times x to the 11th minus 1. And with this formula in mind, we're able to calculate that x equals 0 and 1. So these will be our points of intersection when we're doing our graph. So we're going to go ahead and start that now. So I'm just going to go ahead and make a graph real quick. X and Y. And then since we're doing the axis of rotation around the y-axis, I'm just going to go ahead and indicate that there with the color red. Okay, so we're going to go ahead and do the axis of rotation as right here. Just go ahead and label that A.O.R for axis of rotation. So now we're going to go ahead and do next is start graphing. So we're going to go ahead and do the y equals x to the 1/3. So that typically will look like this. So this becomes y equals x to the 1/3. And then we're going to go ahead and graph our y equals x to the 4th. So I'm just going to go ahead and do that in blue here. So since x to the 4th is an even power, it's going to be similar to a parabola, but more with a flatter bottom. So we're just going to go ahead and do that right here. I'm going to go set that right there. Also draw that right here, just so we can get an indication of what the graph actually looks like. Something similar like that. It's not perfection, but it's close enough. And then just so we remember, we have our points of intersection here where x equals 0 and x equals 1. So we can see that we have x equals 0 right there. We're just going to go ahead and indicate that this right here, where they intersect, is at x equals 1. And what happens is when we plug x into x equals 1 into either formula, oh, let me go ahead and write this down, I forgot to. So y equals x to the 4th. So when we plug in 1 into either of these formulas, we are always going to get the number 1, so that the point of intersection where this intersects is 1, 1. All right, so to continue, now that we have our points of intersection, we went ahead and graphed. Now what we have to do next is start using our rectangles. So just so we remember, the rectangles are always drawn parallel to the axis of rotation. So our axis of rotation is right here on the y-axis. I'm going to go ahead and draw that rectangle right here. It doesn't have to be perfect, as long as you get the right idea. And this rectangle is just called distance x. Now to determine where our r and h is going to be. So remember what r is. R is equal to the distance from the axis of rotation to the rectangle. So that's going to go ahead and be this distance from right here to right there. And that becomes r. And then this right here is going to be the height of the rectangle. So from right there to right there, it becomes h. So now to calculate r, we can see that our axis of rotation is right here and the rectangle is right here. So that distance is traveling from here to here is x. We do not know that distance, so we're just going to go ahead and call it x, but that's how the distance is from the axis of rotation to that. So we're going to go right, r equals x. And then this right here for the height of our rectangle, since it is in between two curves, we're just going to go ahead and make that f of x minus g of x. And right here we can see that y equals x to the 1/3 power is above the y equals to the 4th, meaning it's a bigger power. So we're just going to go ahead and write h equals x to the 1/3 minus x to the 4th. And there now we have our radius and our height. So now what we're going to go ahead and do next is we're going to go ahead and start plugging that into our volume formula. So just so you remember, volume equals the integral from b to a of 2 pi r h dr. And then we're going to go ahead and plug those numbers in. That's going to go ahead and equal. So our bounds are from b to a. And that will be, since everything is in terms of x, it'll be from 0 to 1. So we're going to put that, so 0 to 1. This becomes 2 pi. And then our r, which is just x. And then our h, which is x to the 1/3 minus x to the 4th dx. So now what we're going to go ahead and do next is we're going to start solving for the integral. So what we can do here is we can pull out the 2 pi since it's a constant and then distribute the x. So that's going to be rewritten as 2 pi from 0 to 1. We're going to go ahead and distribute that x now. X times x to the 1/3 means it's adding. So we're going to go ahead and add 3 over 3. So that's going to be x to the 4/3. And then we're going to go ahead and add that one. So x times x to the 4th, we're adding. So it's going to be negative x to the 5th. I'm going to go ahead and dx. Okay, so now we're actually going to continue the integration process. So now this will equal 2 pi. And then if we go ahead and do integral rule, so we're going to go ahead and add 1. So that's going to be 7 over 3. We'll go ahead and drop down this reciprocal, or x to the 7/3. This is going to be subtract. And we're going to add 1 to that as well. So that's going to be 1/6 reciprocal, x to the 6 dx. Okay, and then we're, oh, sorry, not dx. I apologize. Our bounds. So that should be from 0 to 1. So we're going to go ahead and evaluate our bounds. So if we plug in 0, we can already identify that everything is multiplied by 0, so it'll just cancel everything out. So we're just going ahead and start evaluating that 1 in there. So it'll become 2 pi times 1 pi, or 1 to the 7/3 power is still 1, so it just becomes 3/7. And then 1 to the 6th power is still 1, so it just becomes 1 minus 1 over 6. And then when we evaluate this to combine them in like terms, this becomes 2 pi, and then we're going to go ahead and multiply this by 6 by 6, so it's 42. This becomes 18. We know the whole thing is going to be over 42, minus, this has to be multiplied by 7, so we're going to put that 7 over there. So now when we go ahead and calculate that, that actually equals 2 pi times 18 minus 7 is 11 over 42, which then equals 22 pi over 42. And then we're going to go ahead and divide that by 2. We're going to get 11 pi over, 42 divided by 2. That comes out to 21. And there you go. That is the volume of the region that we rotated around with the rectangle on the y-axis. So it's simple as that. And now we can go ahead and move on to the next problem. Okay, and now moving on to the second problem. So we are going to try to find the volume of the solid generated by revolving the region bounded by y equals 6 over x, y equals 3, and y equals 6. So I've already done the liberty of drawing that graph out. So we just want to make sure that we always label the axis of rotation first. So I went ahead and did it on the x-axis. And then we went ahead and graphed y equals 6 over x, which is very similar to y equals 1 over x. That is depicted right here as the blue line. And then over here for y equals 3 and y equals 6, we have that right there as well. So now we're going to go ahead and do first is just find and label those points of intersection. So when y equals 6 over here, and this is y equals 6 over x, so it'll be 6 equals 6 over x, x will then equal 1. So that essentially will give us this point right here. So that is labeled as 1, 6. And then this point over here, when y equals 3, so it'll be 3 equals 6 over x, x will have to equal 2. So this will be over here. This will be 2, 3. Okay, so now what we're going to go ahead and do next is label our rectangle. And we just want to make sure that we always make it parallel to the axis of rotation. So as you can see here, the axis of rotation is on the x-axis. So I'm just going to go ahead and draw that in right here. Okay, and we're going to go ahead and call this rectangle y because it is on the y-axis going horizontally since it is parallel with the x-axis. So now what we have to do next is identify our r and our h. So to do that, we're going to go back over here. So if you recall, r is the distance from the axis of rotation to our rectangle. So we're going to go that right here. So that's right here. That distance is r, and then the height of our rectangle is right here. So that is our h. Okay, so now to go ahead and describe that. So for our r, we can see that this distance will be from right here to right here, and we can see that distance is y. Since we don't know the exact distance, it'll be from right here to right here, so we're gonna go ahead and label that. And then our height, so that'll be going from right here to right here, and that could be described as basically 6 over y. So we're going to go ahead and rewrite that. So as I did over here, x equals 6 over y, because this rectangle touches that curve. So it's going to be 6 over y. So just want to go ahead and memorize our formula. So that is our formula to find the volume utilizing the shell method. So now we're going to go ahead and start setting that up. So we get v equals from the bounds. Since that is b and a, since we are referring to the y-axis, that is actually going to be from this distance right here, y equals 3 to y equals 6. So we're going to go ahead and write 3 and 6. And then we're going to go ahead and start plugging the rest of our information in. So we have 2 pi, and then r is just y, and then our h is just 6 over y. So to basically go ahead and start doing that, just put dy as well. So now we're going to go ahead and start evaluating this. So just go ahead and rewrite this and make sure we pull our constants out. So from 3 to 6. And then we can see that the y's are just going to cancel out here. So we're just actually going to end up with just a 6. So we do 6. Sorry, my pen's running out here. dy. Go ahead and swap that pen out real quick. So it's just more legible. Okay, and now we're going to go ahead and evaluate that. So when we go ahead and do that, it should just become 2 pi, and then multiply the value of 6y. All right, go ahead and evaluate that from 3 to 6. So we're going to go ahead and plug that in first. So it'll be 6y, so we're going to go ahead and do the 6. So 6 times 6 is 36. 36 times 2 pi is 72 pi. And then we're going to go ahead and subtract that. We're going to go ahead and plug that 3 in. 6 times 3 is 18. 18 times 2 is 36. So it just becomes 36 pi. And then when we go ahead and subtract all of that, that just comes out to 36 pi. And that is the volume of our region right there.